So okay, now if you turn down the input again to the input low state, right? So what happens is that you no longer have the integrate here, so this guy remains in current state. This one now have both integrates in here, so you switch this back to the BP state, right? So now you have the output plus high here, all right? And when you switch again to the input plus, right? Now you switch the upstream bit here. So you get the idea. So basically, these two latch gonna take turns switching each other's state depending on which input you're coming in, right? And so you go like this. You can complete a cycle in which you can go back and forth between two states using the same cycle input pulse. And if you look at it as a whole cycle, you can have the overall device in which you have the 4 different states and 4 different transition steps. Okay? All right. And so what we have shown so far is that we haven't built this completely yet, but we have built this thing. So basically the difference between this one is a complete Pavlov flip-flop that we want to build, and this one is an experimental system that we have shown so far, is that you don't have this efficiency here, so you can't complete the circle yet. But what you have is that here you can go to the 4 state with the 3 transition steps, and here I put the output genes here to the blue latch here so that we can read out the state. In this particular system, I used the BXD1, the same enzyme set that I showed you earlier on, in the blue and the purple, and it is another type of integrase gene in the blue one here, right? And I have the ATC and arabinose control the upstream of the integrase in the 2 cases. So what we have here is that we should be able to go between the green and to the red, and remain in the red, and push back to the green again if the system works as expected, right? And this is what we show, right? It's not really clean yet, but you can see the trend. You start in the green state. You induce it with ATC, which is basically induce the plus input, and so you push it toward the red state here, right? And when you induce with the minus input, which is arabinose in this case, you don't see much change, so this thing just split between the one that already successfully flipped to the red and the one that doesn't switch yet, right? But when you induce the second time with the ATC pulse, now if you look back here, right, you're supposed to push back to the green state here, and you see the trend that this guy get pushed back toward the green state again. Right. So the significance of this is that even though it's not a complete cycle yet, what you have is that this is the first time that we connect the 2 bits together, even though one bit is not visible in this case, using 2 different integrated in a system. And it's the first time that we show that we can use 1 bit to drive the other bit. So I haven't mentioned that in the earlier work that we showed, we have excisionate expressed in the much higher copies. You have excisionate expressed from the high copy plasmid, while we have the side that we flip the DNA on the chromosome. Right? This is the first time that we put everything on the chromosome and show that at least the thing switch in the red temperature switch. Okay. So in conclusion, we show that we try to convince you that the in vivo data storage device can be used for studying and controlling biology. The goal is to access to more state and make it more reliable. Right? Our achievement so far, we built the first reliable modular bits that operate at DNA levels. We, to some extent, show that we can use storage hindrance to access to more state by controlling activities of the recombination site. And we built half a flip-flop, which is the building block for the combinatorial counter. So let's thank my advisor, Wendy, a member of the lab, and particularly Jerome Bonnet here, who do the pioneer work on building the rewritable memory, the first part of the project. Thank you.
So let's say you want to store 100 bits or something.
Mm-hmm. Yeah.
Wide.
Yeah.
Do you think you'll need 100 different
Yes.
Yeah.
Yeah. So
or do you think you can be clever and just have let's say 2, but use that putting the site inside of another site.
Yeah, we have explored those ideas too. So it's also depend on like when you say like 100 state, right? You want to make 100 state counter, or you just want to make a 100 state storage, or 100 bit storage. I mean just store like one input and come at once.
Let's say
just different case.
100 bit
yeah.
counter.
So we have explored too. We haven't got like we have got a different kind of design that we sketch on a piece of paper, right? But we haven't got the one that's simple enough that we decide to work on yet. The second part of the second project that I talk about, having a controllable recombination site. Those parts are interesting in the sense that we are also trying to show that you can use the same blocker to block different recombination sites, different recombinase. And for the same recombinase, you can have different blockers to block it. So you can imagine that, let's say you want to have like 20-bit storage, right? You can have like 5 by 4. You can have 5 different recombinases and 4 different blockers, and different combination of them allow you to address individual bits. So we're working on that a little bit, but the 3-state device I showed you early on is good in the sense that it allows us to at least saying if we have any shade at all in the activities of the recombination site. So that's why we should run that first.
So you're inserting these things into the genome of the organism, right, or the cell. Yes.
Excuse me?
You're inserting these things into the genome of the cell.
Yeah. So for the first part of the project, the writable memory, those one, the data registered in the recombination site, the promoter, those one is embedded in the genome, in the chromosome of the E. coli.
Okay.
The integrated exogenase generator for those parts is expressed from the high copy plasmid. So it's also in the cell, but in the plasmid, right? It's not in the genome. One thing that we also trying to do is to try to figure out if we can put everything into one piece of DNA to make it more compact, right? And what I show you in the third project is that it's the first step how about that, because like it's the first time we show that we put exogenase and the recombination site on one piece of DNA, and we can still see some trend of switching. That's correct. Yeah.
If you want to multiply in binary by 2, it's a very cheap operation. Are there certain operations in your system that are really cheap to do?
Multiply
by 2, for example, you just add a 0 and you shift all the bits. Are there operations in your system you can do on your data that are really cheap to do?
Yeah, we haven't thought about it clearly yet, but if you talk about cheap in terms of like the number of parts or the energy that you consume.
Easy to do.
Easy to do. So there should be a pretty simple way to do. We haven't explored that part extensively yet. Yeah.
I have a question. In your conclusion part, you said you can use this to study and control biology. I can understand you can control biology. What kind of system do you want to study?
Okay. So for just the simplest memory, just like the DNA inversion memory, the first work that was done is actually back in 1985, and people use it to study the DNA damage in the cell. I think it's a different type of memory that we have, but the idea is the same. So they want to study whether or not the cell has been exposed to DNA damaging agent, right? And they hook up the input to the memory with the mechanism inside the cell, which is going to be active during the DNA damage, right? So you can imagine that when the cell exposed to DNA damage, there's something changing the cell for a moment, right? If you don't catch it in that moment, and you don't have memory, then you don't know what has been going on in the cell at that time, right? But by coupling those sensors for DNA damage to the memory, then that system allows you to say that, oh, okay, this cell has been exposed to DNA damage at some point in the past, even though right now, like the physiological state that reflects DNA damage is no longer there, it's no longer present. So basically, it's most of the time when people talk about studying what happened in living cell, right? They talk about, okay, we want a good sensor to sense what's going on. We want a good reporter to tell what happened, right? But in many scenarios, in the case that the process happened in a very short time window, or in the location that you can access real time, let's say inside the body or whatever, right? So the memory access function as a surrogate in the sense that it can keep those information of like what happened and report back to us later. Yeah.
All right. Any other questions? No. Let's thank Popcorn one
Thanks.
more time.